Okay, we're on. All right. So from your glorious reading, Silence of the Lambs. From it is. From your glorious reading, if you did the assignment, shouldn't have been too bad. I'll highlight some things, but you could have histograms, and from the histograms, you could draw a curve that kind of let me change the color that goes along with this histogram. In the area under that curve should come close to equaling the area of the boxes of those histogram values. And then it goes on further to say that if these boxes were even closer together, like smaller, then the area under the curve gets closer and closer to being exactly the area of the boxes. So the smaller the boxes are, the better representation those two areas are equal to each other. And of course, this one I colored in red. This is a skewed left. Remember we talked about that. And then area under this curve would be equal to the area of these boxes, or at least close to it. Right? Blah, 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 blah. So what we're going to lead to is, these are called density curves. And that area also actually represents the percent of data, when we talk about a normal curve when we get to it. And we'll make that happen here when we move on with the notes. Okay, so what we're going to get to is normal distributions, which there are symmetric scenarios, but there's also more to it than that. So let's just hold off on that. There's our little message. Non-normal distributions, which we don't know the difference yet, so just hold off, uses a density curve to represent all of the data. And then if we're dealing with all of the data, all of it would be 100%, so the area under the curve represents all of that data. So the area under a curve in these scenarios will always equal to 1, the total area, because that's 100% of the data that's covered in whatever scenario you're looking at. Right? I don't know if I explained that perfectly, but let's look at our next example that's not normal. You don't know that means yet until we get to it. All right, so here's a density curve, and then the example up there, density curve shows the distribution of time in minutes men spend on the phone in a week. Okay, so here's this curve. This is the area under the curve, which actually is represented by also the percent of men that do these amount of minutes on their phone. So down here, these are in minutes. 150 minutes, 210, 275 minutes, 320 minutes per week. I'm like 0 minutes per week. I don't like talking to anybody. Anyway. So, first things first, silly little question, there's a missing value. What should all of these add up to become, since it's the percent of men that do whatever they're doing? 1. So the point of having something missing there is you demonstrating that idea, that you know that these should all add up to 1. So the missing value is 1 minus 0.18 minus 0.20 minus 0.3 minus 0.08. And that will get you what the remaining is. Yeah! I'm out of practice. So one person out of 30 got 0.24. Did you get a second person? Hallelujah. That's just a word of rejoicing for any particular reason. Okay? All right. And then what percentage of men spent between 210 and 320? Well, that's what we're looking at right there. What's the answer? We can all do that one, right, without doing the calculator? 0.54 or 54% of the people. Okay, hold on, we get a visitor. Maybe, I don't know. That's true. Okay, now it's time for normal distribution. So we finished that one off. That was all big fun. Had good times. All right. So normal distribution, obviously you see is symmetric. Okay, and I'm terrible at this letter, but what letter is this a bad example? Me? Isn't it mu? Mean. Oh, but it's mu, the letter, right? Mu. But it's mean. So that's the mean. The mean is right in the middle. So a normal distribution, those that have had this before, I know. Mu is right in the middle. I'm going to zoom this back because that's large enough. I can't do it either. Are you doing mu? I can't do mu. But then the pen doesn't release. Then it gets that little extra squiggly in there. Are you okay? Well, get up. Let's go. All right. You look like a little. All right. And then this is lowercase sigma, right? And that's the standard deviation. So this is the mean. Oh my gosh, my pen's not writing very well today. And then standard deviation. And we actually did this when I did that Algebra 2 standard deviation when we divided by n, remember? Then the next day I made a big idea of yn minus 1 and showed that. But what we did is, whatever the standard deviation is, one standard deviation to the right and one standard deviation to the left would be symmetric in a normal distribution. So this is mu plus one standard deviation. This is mu, whatever mu is, minus the standard deviation. Oh, and I feel like I'm writing worse than I did first hour. This pen's just not really working very well. Then when I go another standard deviation to the right, that's symmetric with going another standard deviation to the left. So these two should end up in the same spot. But there's more to it than this. Just hold off. Minus 2 standard deviations. And then a third one. Mu plus 3 standard deviations. Mu minus 3 standard deviations. Okay, there's more. Right? A normal distribution is also distributed exactly the same for every type of situation by, I guess, what's called the empirical rule, which is the 68, 95, 99.7 rule. Now what I did, I snapped out of our Algebra 2 book the same idea. Now they use X with a line above it to demonstrate mean. Remember that was for a a sample scenario, but don't worry about getting those two confused. It's the same idea. Here's what the 68, 95, 99.7 rule is. In a normal curve, not only is it symmetric, this holds true. That 68% of the data is one standard deviation away from the mean. That means 34% of the data is one deviation to the right, 34% of the data is one deviation to the left from the mean. 95% of the data is two standard deviations away from the mean. That means, well, now we got to do some math. Here's the 68%. They have 95% of the data be from here to here. That leaves 13.5% in these little positions. Go ahead and mark that down. 99.7% of the data falls within 3 standard deviations of the mean. If you do the math, the difference between 95 and 99.7, that leaves 2.35% of the data between the second and the third standard deviation from the mean. So these are what hold true for any normally distributed situation. Right? And then that leaves 0.3% left. Anything past 3 standard deviations, there's only 0.15% of the data. And then same thing on the other side to the left. So we got to mark these on anytime you see normal distribution. this is what holds true. It's more than just symmetric. These percentages are true. All right? And that's what we're going to need to focus on. Okay, then I put some normal curves together just to give you some points that were also made in the book that are true. I put two situations where the mean was the same, 100. But one of them I said means 100 with a standard deviation of 20 compared to a mean of 100 with a standard deviation of 5. Just to throw another thing at you, the difference between tightly packed data or data that's more spread out. And what happens with the normal curve when it's more spread out. So here we go. This is how we do it. And this is how we're going to do our next example with numbers. The one in green is mean of 100 and a standard deviation of 20. So one deviation to the right would be 120, right? You add 20. A second deviation to the right would be add another 20. And then the third deviation, add another 20. So 100, 120, 140, 160. All right, and then the other way, subtract 20, subtract 20, subtract 20. Well, that normal curve would be shorter and wider because the data is more spread out to get 34% of the data between here and here, and 34% of the data between here and here as far as an area situation is concerned, because that's what also emulates this. As opposed to only a standard deviation of 5, putting these two together, this one, 100, 105, add 5 again, 110, add 5 again, 115, we're done. You know, that's the third deviation to the right of that. So this normal curve would be much higher in order to draw that one and get those percentages as far as the area is concerned to work out that way. So the more tightly packed the data is, the smaller the standard deviation, the taller and skinnier the bell curve is. And that was something in the reading as well. Just thought I'd throw that at you before we actually do a question that pertains to this whole situation. All right. So here it is. Go ahead and give yourself a chance to write that down. As you read this, we should keep this in mind up here. Adult IQ scores are normally distributed with a mean of 100 and a standard deviation of 15. As soon as you hear that normally distributed situation, you don't have to worry about how high and how low based off that last thing I just told you. You know, all your curves might end up looking the same. That's fine. Okay, but what we want to do is go right in the middle, do a hundo, and maybe draw our normal, what would be called a bell curve. And then we're going to break it down appropriately. So the standard deviation is 15. Remember, we did this last week when I gave you that Algebra 2 example of standard deviation. If we have a standard deviation of 15, that means when I go from here to here, one deviation to the right, this is 115. You add 15. Add another 15, you get 130. That's the second deviation to the right. Add another 15, that's 145. That's your third deviation to the right. And then you also have to go left. I'm going to cut this in half right here. Oh, I thought I lost my pen. I was about to go ballistic. All right, I did lose it first hour. I had to restart and start all over. They loved it. Okay, one deviation to the left is 85, right? Check my math here. It's far from perfect. Just ask my wife. 15, 70. And then what's 70 minus 15? 55? What are you looking at me that way for? 55? Odd look from a student. Okay, here we go. He's trying to help. All right, so what percent of the data falls from here to here? It's right up here, everybody. 34. I'm just going to put 34 there. Not 0.34. We know those are percents. If we have to use them, we'll change them to decimals. And what percent of the data falls here? 13.5. And what is percent of the data here? 2.35. If it's normally distributed, this is the case. Just remember, past this is 0.15%, very small. 13.5, and then 2.35, and then 0.15. Then you can answer silly little questions like this. Find the probability. Remember, this all adds up to 1. Actually, 100 in this case because I'll put it in percent form. All right? So find the probability that a randomly selected adult has an IQ of, or an IQ that is, in this case, between 700 or 70, and 115. Boop. Blah, 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 blah. What do I do to find that answer? Just add them up. Add them up. Go ahead and add them up. Add them up. Anyone know that song? Oh. All right, you shouldn't have swear words in it. Can anyone add those up? Is it 81.5? Can we get a heck yeah? That was on? Oh. All right, 81.5%. Okay, and then for the next one, isn't this Mickey Mouse? Now that we've done this. More than 85. More than 85 is all of these. Isn't this fun with the coloring? So I can either add all these up. That's one way to do it, and that's the way I'll do this one. The other one, I'll do the opposites, because it's even more that you'd have to add up. And I'm sure we can add. I'm sure you get it just from this, and you don't need me much anymore. First bell already rang. Want to give you some time. We can all add that up and get what we want to get. All right, right? You don't need me for that. Then the last one says less than 130. Less than 130 is all of these. A faster, more efficient way would be to do what with this? Yes? From one, actually it would be 100 in this case. In this case, it would be 100 because of what I've done with the percentages. Okay, so 1 minus the opposite of that, right? And then just, this is a real simple question for this one. And you can do the math on that. You don't need me for that. You can't subtract. What are you doing in here? All right, IQ between 140 and 145. But look at what it says. If you select and survey 1,500 adults, how many would have an IQ between 100 to 145? Well, this one we better turn these into decimals, because that's how you deal with percents, actually, when you have to multiply it, which I hope you understand you'd have to do that. So 34% plus 13.5% plus, now what's 2.35 become? This drives me nuts. 0.0235. To not know that still as a senior in high school. All right, and then you're going to multiply that by 1,500, and that's how many would be out of that, right? You get that? Is that good? You okay? Because I can be done then. All right, and then you guys can find the numbers from there. You okay? Give me a look. All right?